Next thing we're going to look at is this thing called concavity. It has to do with concaveness. Okay, is another way you could think to say concavity. Which way is our graph concave? And there's two ways: concave up, okay, which means it's curving up; concave down, which means it's curving down. So concave up, if we look at our first derivative, okay, which is our slope of our tangent lines. Here I've got a negative slope for my tangent line. Here's less negative. Now it's positive and becoming more positive. So my first derivative is increasing. It's going from negative to positive. So since our first derivative is changing, okay, and is becoming more positive, so it's a positive change. Okay, so our second derivative, which describes the change in our first derivative, okay, our first derivative is changing in a positive way, so our second derivative is positive. Concave down means my first derivative is decreasing. It's getting smaller. So here I would have big positive, smaller positive, 0. Then it becomes negative, more negative. So it's decreasing, which means my second derivative is negative, because the change in my first derivative is a negative change, so that means my second derivative is negative. So concave up and concave down means, and so when we're drawing these, it's going to help us decide which way our graph is curving at different points. Now, much like we did with our first derivative, we're going to look for these certain points where our second derivative is 0, but now they're called points of inflection. And that's where the graph is changing from concave up to concave down. So here's concave up. At some point, I'm changing and becoming concave down. This point where it changes, where it stops curving up and starts curving down, is a point of inflection. And it can either go from positive to negative, or from concave down, which is negative, to concave up, which is positive. Okay, here would be my point of inflection, the spot where it changes. We also have a second derivative test. Okay, so it's just like our first derivative test. We're going to use it to test points that are left of our points of inflection and right to see what's happening. So to see if, because I know it's changing here, this is where it's 0, but is it changing from positive to negative or negative to positive? So I'm going to test areas on both sides to see which change is happening. So let's start with a couple examples here. So I need to know the first derivative in order to get the second derivative. So the first derivative here is going to be 6x squared minus 6x minus 12. Second derivative, I'm going to take the derivative of the first one. I'm going to get 12x minus 6. So, I also want to mention back here, points of inflection are also where this is undefined too, just like the first derivative. So I need to look where this is either 0 or undefined. I'm not dividing by x, so I'm not going to have any undefined values. So I just need to find out where this equals 0. So add the 6 over, divide by the 12, and I get 1/2. So when x is 1/2, that's my point of inflection. That's where it's going to change from concave up to concave down, or from concave down to concave up. I don't know which one it's doing. Okay, so here's 1/2. It's either, doing something like this, or maybe it's starting this way and then switching there and changing to go the other way. In order to find out, I'm going to test a point. I'm going to test maybe 0, because that's left of 1/2. I'll put 0 in here. I'd get -6. So I'm getting a negative second derivative. Negative tells me it's concave down. Okay, so it's curving this way. Test a point to the right of 1/2, like 1. I'm going to get 12 minus 6, which is positive, which means it's curving up. So it's more like the red one here. So if we look at the actual graph, let's zoom out here. Okay, this is the graph of our original function. Here's concave down, and then right here, where it's 1/2. Okay, so right around this area. Okay, it was curving down. Right here, it's going to stop curving down. So my slopes are going to stop getting more negative and start getting less negative again. Okay, it's going to start curving in an upward manner. Okay, so that's a real basic example. Let's look at something a little harder. Okay, so I've got this one. I think I actually want this square root bar to go a little further. So I need the first derivative, which is going to require the product rule. So I'm going to take first times derivative of the second. Okay, derivative of the second is going to be 1/2 of this thing, lower the power by 1, times derivative of the inside part, which would be the derivative of just x, which is 1, so I don't need anything extra, times second, times derivative of the first, which is 1. Let's simplify this a little bit. So here I'm going to have x over 2 times the square root of x plus 1 plus the square root of x plus 1. Let's get a common denominator, so I'm going to multiply the top and bottom by the square root of x plus 1 and 2. So that's going to give me a common denominator that will allow me to actually add. So this is going to turn into 2 square root of x plus 1 times the square root of x plus 1 is just x plus 1. So I'm going to be adding 2x plus 2 over this. Combine like terms. I'm going to get 3x plus 2 over this. Okay, and that's still my first derivative, so now I'm going to take the derivative of this to get my second derivative. So that's going to require the quotient rule. So bottom times derivative of the top, which would just be 3. So I'm going to turn this just to a 6 here. Okay, so that's bottom times derivative of the top minus top times derivative of the bottom. Okay, derivative of the bottom is going to be 2 times, drop the 1/2, x plus 1 to negative 1/2. Simplify this, over bottom squared. So the bottom squared is going to be 4 x plus 1. So let's see how we can combine this. I have 6 squared of x plus 1. These will go away. Okay, I'm going to split this up actually and give them each their own denominator. And this is going to be 3x plus 2. This moves down to the bottom. So again, let's get a common denominator here. Actually, if I just reduce this, because this is x plus 1 to the 1/2, this is x plus 1 to the 1. So if I subtract my exponents, I'm going to get 6 on top, 4 square root of x plus 1. So all I really need here is a 4 on the top and bottom. So that's going to give me minus 12x minus 8. Reduce everything by 2 and combine like terms here. So 6 minus 8 is negative 2. So I'd have negative 12x minus 2 over 4 square root of x plus 1 reduced by 2. I get negative 6x minus 1 over 2 square root of x plus 1. Okay, that's my second derivative. Okay, so points of inflection, I need to know when this is undefined. Looks like when x is negative 1, it'll be undefined because that'll make me divide by 0. And really anything that's less than negative 1, so like negative 2, negative 3, negative 4, all those are going to make this imaginary. So those don't even work. In fact, in our original function, those wouldn't work either. Okay, this graph starts at negative 1. So starting at negative 1, which is also a point of inflection, which really isn't going to matter because it can't change from anything if nothing's happening to the left. So I can pretty much ignore this point of inflection and just find out when this thing equals 0. So when the top equals 0, which would be when x is negative 1/6. So it's a point of inflection. I need to know, is it going from down to up or from up to down? So I'm going to test a point to the left of it, which would be like negative 1/2. Okay, if I put negative 1/2 in here, I'm going to get positive 3 minus 1 is positive 2, so that's positive. Negative 1/2 in here plus 1 is going to be positive. Square root of a positive is positive times 2 is positive. So I've got positive over positive, so it's positive on the left, which means it's concave up on the left. And on the right, if I put in a number like 0, I'm going to get negative 1 over, so I got negative over a positive, so it's going to be negative on the right. So it's changing from up to down. Okay, and that's the concavity. All right, let's look at a trig function. So this one's going to be pretty interesting, actually. So first derivative. Okay, so I'll leave the 2 out. Derivative cosecant is negative cosecant of the same thing times cotangent of the same thing times derivative of the inside part, which is 3/2. Combine these, I'm going to get negative 3, so the negative from here with these is negative 3. Cosecant of this times cotangent of this. And that's the first derivative. Second derivative is going to require product rule. So I'm just going to leave that negative 3 out until I finish the product rule. So derivative cosecant again is, it's product rule. First, take the first times derivative of the second. Derivative cotangent is negative cosecant of the same thing times the derivative of the inside part plus the second thing times derivative of the first, which again is negative cosecant cotangent, times derivative of the inside part, which is the 3/2 again. So let's distribute the negative 3 and combine it with these other numbers. Or actually, let's just take a 3/2 out. Okay, I can take a 3/2 out because it's in both terms here. And I could also take out a cosecant, because I've got a cosecant here and a cosecant here I can take out. Oh, and actually this is squared, sorry. This derivative of cotangent is negative cosecant squared. So I'm going to take that out. So when I take the 3/2 out, that turns this into a negative 9/2. when I take out a cosecant, and I'm going to take a negative out because I've got negative here, so that makes this positive. That leaves me here with just the cosecant squared of 3x over 2 plus cotangent. Cotangent is cotangent squared of 3x over 2. I want to know when this is 0 and when it's undefined. Well, in order to get 0, I've got this times this, so I can set each one equal to 0. Okay. And cosecant is 1 over sine. And the sine can be 0, but 1 over the sine can never be 0. That's like saying when is 1 over x 0. It's never 0. So I'm not going to have an answer for when it's 0, but I will have an answer for when it's undefined. Okay, because I need to ask, when is my sine 0? Well, my sine is 0 when I take the sine of 0 or pi. So when is 3x over 2 equal to 0? Well, it equals 0 when x is 0. So since if I put 0 in here, I get an undefined value. That's a point of inflection. When does 3x over 2 equal pi? Well, if I multiply by the reciprocal here, I'm going to get 2 pi over 3. Okay, so there's 2 points of inflection. And I'm only looking for the ones in this area, so I don't have to worry about, big multiples. This thing here, I need to know when this is going to equal 0. If I change it into sine over cosine, oops, that's a plus. This is cosine squared over sine squared. I can multiply both sides by sine squared to get rid of my denominator. So I'm asking, when does 1 plus cosine squared of 3x over 2 equals 0? If I solve this, I'm going to subtract the 1 over and then square root. And I'm square rooting a negative, so it's never going to be 0 because the only answer I'm going to get are imaginary answers. So it's never going to be 0. Is it ever going to be undefined? Well, the undefined values are actually going to be the same that I got over here. So these are my points of inflection. Actually, I should have another multiple here because in order to get pi, I could put another one in here. So when does it equal pi or pi plus or minus, a 2 pi value? So if I, okay, this is kind of a trig review, but remember, because I want to know when it's pi or a multiple of pi, and these are going to be multiples of pi. So now I want to multiply both of these by 2/3. So if I add another, so if I multiply this by 2/3, that becomes 4/3. So if I add 4/3 pi onto this, that's going to be 7/3. So 7 pi over 3 is another spot where it'll be undefined. If I add another 4/3, that'll bring me up to 11/3, which is actually beyond where I want to go. I think I did that right. And this is a past 2 pi, so that one doesn't count. But this one, I want to add 2 pi onto this one. And when I multiply that by 2/3, I get 4 pi over 3. So that's another one. There we go. If you have questions on that, you can let me know tomorrow. But these are going to be my critical points. And let's just look at the graph of this. I think I've got it typed in here already. Yep. Here's the graph of my original function. Okay. And if you notice, okay, here's 0. Here's 2 pi over 3. And that's actually a vertical asymptote, but if you notice right before the vertical asymptote, it's concave up, it's concave down, it's concave up. So this is 4 pi over 3. If we do our second derivative test, we should see the same thing. So 0 isn't really a count because that's the beginning of my range that I'm looking at. So I can ignore that. But if I plug in a value less than this, like pi over 3, if I plug pi over 3 in here, pi over 3 would be, that'd be 3 pi over 3, which is pi over 2. The cosecant of pi over 2 is 1 times 9/2 is positive. Okay, times here I'm going to get a positive because it's squared plus a positive since it's squared. Okay, squared always makes a positive. So I got positive times positive, which is positive. So it's concave up to the left of this. And if I put in a number past this, like 3 pi over 3 up here. So 3 pi over 3, which is pi, is 3 pi over 2. The cosecant of 3 pi over 2 is negative 1. So I've got negative times positive, which is negative. So it's concave down on the other side. Okay, and then on the right side of this, because this is left side, on the right side of this, so if I plug in a value like 6 pi over 3, which is 2 pi, if I put 2 pi in here, I'm going to get 6 pi over 2, which is 3 pi. Cosecant of 3 pi is, let's see, 3 pi would put me back at pi, which would be 0. I guess I picked one where it's undefined, so I'd have to pick another one, but it's going to turn out to be positive also. So I know this last one with the trig is a little confusing, but if you want, I can do another example in class tomorrow. But the basic concept is find your points of inflection, set them equals 0, find where they're undefined, and then it's basically the same thing as your first derivative test.